that we're expecting to, so we'll go ahead and start the movie. Alrighty, so we're coming up to our last few topics in the class. If we go ahead and take a look first at our course flow here, we're going to be working on principle of virtual work. I did have a couple people on and ask me if that meant a virtual class day for the resident folks, but so I added principle of in front of that just so we're clear. But we're still in here. We still have some people, so that's good. Then we'll do our Rayleigh-Ritz method. That's going to cover all of the stuff we need for energy methods. So that's going to be part of homework 5. So then we'll also go over the homework 5 problems that we can do. The last new topic that we have left in the class is going to be next Monday, thermal expansion, and then thermally driven buckling. So that's going to be our last new topic. Then Wednesday, we'll go over some relevant and current fleet issues that are related to the topics that we've looked at, like torsion and beam bending and strain measurements and things like that. And then we'll keep chugging along on our homework. On 8 June, we're going to have our final regular class period, homework number 5 review. That'll cover everything we need for the exam, which is going to be energy and thermal stuff. And then on Wednesday, 10 June. So we're on pace right now to finish up our last class block on Wednesday the 10th. I'm just going to hold that 15th for now, just in case, but I don't think we'll need it. Not affecting our class, but for resident folks, if you have any classes on Tuesday night, they are most likely going to be canceled. They'll be officially canceled once some reservation gets completely formalized. But if you want to start penciling in something fun to do on that day, after you muster, of course, then you could think about that. It won't affect us because we're not meeting on Tuesdays, but just so you're aware, I put it on there. That's a staff and faculty wide meeting that would mean no classes. So we're going to jump back in where we left off on our slides talking about multiple loadings and dummy loads. There's going to be a continuation of our energy method stuff. All right. I'm not quite done with all of the exam 2 gradings yet, and we have a few stragglers out there as well. But since I plan on sending it to you later this week, I want to let you know about one additional column that'll show up. If you already took a class with me, you know about this. But in addition to the stuff you saw in the last one, where you have the average to date, this time it'll have 75% of the way there. It'll have the homework exam, what does it do? And then you'll get 4 blocks, which really don't show up at all on this screen, but probably for the recording, they'll be fine. Some gray colored blocks. There we go. Now we can see them on the projector. So what you'll see right here is what you need to score on the 3rd exam for the average to come out in these 4 things, okay? So for a lot of you, these numbers are going to be very low. Some of you might not even have to show up if you just want to be. I'd still recommend that you do, but that's what these 4 numbers are going to be on your second scoring sheet. Okay. So for those who just joined, the 4 gray blocks that you'll get later this week when I send out the scoring sheet will be what you need to score on the last exam in order to get those averages listed. All right. For most people, these won't be impossibly high numbers to get. All right, let's jump on over to our 6.3 slide set. And where we left off was we had gone through and we'd looked at all the different individual deflections from what we know about axial and beam bending. And we were able to see that they did add up to the same thing that our Castigliano method gave us. All right, so we got pretty high confidence in that now. All right. We also said that if we needed to find out something that we didn't have, we could add a load on there called a dummy load. So we're just going to formalize the steps for that. So for our dummy load method, we want to determine the displacement or rotation anywhere along the structure if we don't have an applied load. Let's say we've got an end load, but for some reason I want to know the deflection and or the rotation at the middle. Maybe there's an issue where with a certain amount of deflection, we could have interference or contact with another part. We just place a load on there, all right? Could be a force or a moment. We can choose the direction as desired. If we're fairly clever, we can guess which way to do it so that we get a positive answer for delta and theta. But if we guess it wrong, we'll just get a negative number. It'll tell us, hey, you should have drawn it the other way. All right. So no big deal there. We can reasonably know from our engineering intuition that this is going to deflect something like that. All right. So if I want to know what the deflection is and the rotation, it's probably going to be going down and it's probably going to be rotating in this direction for theta and delta. So I might as well put my dummy loads on like that. So you stick them on there, treat them just like any other load and formulate your energy. And then after we take our Castigliano, which is delta, partial energy, partial load, we'll set du df delta dummy force equals delta and du d dummy moment equals our theta that we're looking for. After we've done that derivative, then we go back and set the load or loads to 0 in that expression. So there's our dummy load method. All right, we treat it just like any other load, and then we zero it back out at the very end. Where the magic happens is when we get the real load and the dummy load combined in that m of x, when it squares, we FOIL it. And so even when we take derivative with this one, it'll be attached to some portion of the real load. And that's how we get our results. We were able to see those product terms come out also in this Castigliano when we were squaring for our moment in there. Let's take a look at a quick example here. We're going to do a truss problem. So let us do one last free body review before we go to Ritt's method, where we won't use the free body diagram. So if you don't like free bodies, right after this will be the time to tune in. All right, let's take a look at this one. We've got truss. It's a 3-4-5 triangle, so it's nice and easy to work with. I labeled the nodes or the intersections B, C, D, and F, so just so we avoid the Young's modulus that we're going to see in there. We got a pin over at B. We've got a roller at point D. Dimensions are, again, make it a whole number triangle. We got 4 on the height, 5 on the diagonal, and we've got an applied load at the top, P. Throw that applied load on there. I'm just redrawing before we jump over. And what we'd like to find out is what's the deflection at that roller spot. All right, we know it doesn't move up or down, but it can slide over to the right. So we need a delta at spot D there. All right, we don't have a load there, so we don't have an easy energy method approach to get it, but we can throw one on there with no problem. So there's our applied load P. We want a deflection down here. So what I'm going to do is throw on a dummy load right here. We could call it F sub D or whatever we'd like, but some dummy load right there. And it's just going to sit right there. We're going to treat it like a load as far as the rest of the structure goes. All right. So now that we've got that one on there, I can figure out what my reactions are. Well, my reactions over here is the only place where I support an X force. So coming back this way, I'm going to have P plus all of that dummy force, right? Is the only reaction that we get in X, right? If I want to grab the vertical reactions, I could do moments about B, let's say. So I've got P times 4 going clockwise, and I've got the reaction at D times 6 opposing it. All right. So what that's going to leave me with, if I do 2/3 of P here, 2/3 times 6, and then 1 times 4, those match up. All right. So if I sum moments around there, I get my reaction right there. And there's no vertical applied load. So if I'm going 2/3 P up here, then summation of forces, I just get 2/3 of P going down. So there's my reactions. There's my applied load. Note that the dummy force didn't factor into these vertical reactions because it passes through where I was summing the moment. So we don't see that one at all. We'll only see it in the X reaction. So here's our setup. And then we just need a few free bodies in order to grab everything that we need. We need the forces inside each bar. So let's do one free body at a time. Free body diagram at spot D first. Right? So for this, what we're going to want to do is just take a little slice around that corner. At this spot, I've got the bar between D and F. So force DF going this way on an angle. I've got all of force CD going this way. I've got 2/3 of P going this way, and I've got the dummy force going this way. Now there's two that I don't know, CD and DF. If I sum up forces in the vertical first equal to 0, I've got 2/3 of P going up, and then I've also got that DF force at 4, 3, and 5. So I've got 80% or 4/5 of it also going up. So I got the vertical part of force DF going up, and then that's 80% of DF. If I take the sign, it's opposite over hypotenuse. And then I got 2/3 of P going up. So my DF force works out at, they're both going up. So that means this one will have to get a negative sign or compression. Got minus 5/6 of that original P load. So we got that one. Then let's hop over to another spot. Let's say go to C right here. Sorry, I need to grab FCD on it. Right. So if I sum up forces in X, I'm going to have minus of FCD. I'm going to have all of the dummy force right there. I'm going to have minus 3/5 of force DF, which we already found, so that can go in there. And then nothing from this one. So force in CD, if I crunch through on that one, I get the dummy force, all of it, plus, let's see, 5/6 and 3/5, so I get a half, 15/30, a half of P right there. So CD is in tension. We kind of figure that's the case because this should be stretching off to the right. And then this one's in compression. If I jump over to spot C, this is going to be a nice one. We don't have to do any sines or cosines because it's all vertical. And I've got force CD. I already solved for that. I've got force BC on this side. And then I've got the force in, call that CF. This one, not too bad. I've already got force CD, so I know that's the dummy force plus a half of P. There's no other forces in the vertical, so this one's just going to have to go to 0. Some forces in Y, and that's the only one. And then over here, they're equal and opposite in the X direction, so BC is also going to carry that same value, dummy force plus a half of P. So I got everything at that node, and it's up to me. I could go to any other spot. I'd like to, either the top or the left, maybe go up to the top. So at spot F, I've got 3 bars, and then I got that force P going this way. Down here, I got force DF. Over here, I got the force from FB, the upper left diagonal. And then I've got force in CF, which I know is 0.
Kind of falling off the screen there.
There we go. Thanks. So I got CF that we found that one was 0 from up here. DF, I got minus 5/6 of P. And I need to get this one right here. If I sum in horizontal, I've also got to include that P there. But if I sum in vertical, all I've really got is the same component both going down for DF and FB. All right. So if they're both pointed down and they both have the same sign, 4/5, SINE, not SIGN. They both have that 80% of it going down and both in the same direction. Then all I do is flip the sign between these two. This one's going to go plus 5/6 of P. So now I got the loads on all 5 of those members. Do they make sense? Well, what it's just telling me is that by pulling over to the right, I'm pretty sure I'm going to stretch this one to the right. So that makes sense. This one's going to get a little bit shorter. That's probably what's going to happen. It's going to tip over a little bit like that. This one's not going to carry any load, and these two are going to stretch out. So I got tension here, tension here, tension here, and compression here. Nothing on now. That looks about right. My triangle is going to skew over, so I expect this part to stretch as I pull it to the right. This one will contract a little bit, and then these will get pulled out. If I didn't have the bottom ones, this would slide off to the right, so they should definitely be in tension. So now we got all the loads on there. It's just up to us to make the energy expression, which isn't going to be too bad for us. So U is just going to be summation of U for the bars that we have. All right. And for our bars, that's going to be F squared times length over 2AE. All right. And we'll assume all the bars are the same. So we just need to go one by one. There's going to be force in DF squared, and that DF member has a length of 5. Right. So F squared, so this is the length of DF. Right. We got F squared, then we got force in CF. Square that one. We got a length of 4 to a. All right, so all these are going to look exactly the same. Force of FB squared. That one had a length of 5 over 2AE. We got the force in BC squared. That's a bottom one, so it's a length of 3. And then we got the force in CD. Did put that one on. Squared 3. And I've got this force, I got this force, I got this force, I got this force, I got this force. In fact, CF was 0 according to a couple slides back or a couple screens back there. So we can cross this one out. So what we're going to lay off is 4. They're all constants because there's no intermediate load. So we don't have to do any integration. There's a little bit of foiling, but it's not too bad. So I'll just skip ahead to our full value here for U. All right, I'll save us the foiling part. We get 250 over 72 AE with the regular load squared. We get 3, the dummy load squared over AE. Then we get another 3 of the real load times the dummy load. That's from the middle of those FOIL terms, the OI terms. OI. Australian terms, maybe we'd call, right, from our FOIL. OI. This is the term that links the real load and the dummy load, and that's what's going to leave us something left on our derivative. And then we got the real load. Something like that, all right, for all the stuff once we combine everything. All right. So we got to take a partial U, partial dummy force. This is what's going to give us what we need. All right. This doesn't have anything with the dummy load in here. This one does. So I'm going to get 6 times the dummy force over AE here. So this one does. This one's all P, and then this one here, P times dummy. Here's the middle of that FOIL term. This is what's really going to help us. All right. So I'm going to get that one. I'm going to get 3 times P over A times E. And now I've got my expression for delta at D in that direction we want to go. Then we're going to set the dummy force equal to 0. Now is when we can plug back in at 0 here. So we can 0 this off. And we see the term that survived was that OI from the FOIL. So my delta, I can say, is 3P over AE. And there's my deflection. Seemed to work out okay. Now, it would be great if we had some idea of that deflection from another formula. So let's think about the force that's inside this BCD member right here, okay? The force in CD and also the force in BC is this, dummy force plus half a P, all right? So the force that's inside BC and the force in CD, in terms of real load, is a half a P, all right? If we didn't have the dummy load on there, I know that these are getting stretched by a half of P in tension, all right? And I know my delta for axial is force times length over A times E, right? So my force, P over 2, my length all the way across the bottom is 6 AE, and sure enough, I get P times 3 over A times E that way as well, right? And yeah, I picked this one so that we had some kind of a backup, some way to know that all that energy jump came out. Now, if it's a complicated structure, you might not get lucky. You might not get an easy way to calculate axial deformation only. It's going to come from lots of different loads. But here we can see the tension that's in there times the length across the bottom. Remember, these are both stretching, so we can count this as a single member across here. Length of 6, and then AE, or they each stretch times 3, and you have 2 of them together, but we get 3P over AE for that one as well. So dummy load method seems to work out. Did anybody have any questions about that process? All right, let's jump back to the slides, and we'll lead on into our Ritz method next. So we're going to introduce this concept called virtual work. Just nothing really too difficult. We're just going to introduce an arbitrary displacement field. Right? Say we're going to define some displacement field. We'll call it lowercase delta U. Right? And that could be in X, Y, and Z, however many directions we need it for the problem. And that means our strain field is going to be same strain displacement relation as we've always had. Our strain energy then, if we define that in terms of displacements, I can have little virtual strains that are made from that displacement field that I picked, and I throw it on in here, and there's my setup, just like the strain energies that we talked about earlier, right? Whatever ones we have active and per volume, we integrate it on. My external work, if I formulate it in terms of that displacement field that I've assumed, I could have some body force times the displacement. That's force per volume, so dV. I could have some kind of a surface pressure per area, or I could have a distributed load per length, something like this, and that's for that whole field. And then I could have concentrated forces or moments at some specific spot. So then that displacement field only at the specific location, right? And for equilibrium, we should say that this internal energy matches the external work, right? Goes back to our physics class where we said change in kinetic plus change in potential plus change in work equals zero, right? Conservation of energy is all we're doing here, right? That says however much external work I stretch out the thing, it's going to be stored internally as some potential or strain energy from all the atoms getting stretched apart like a spring. And what we're going to say is we're going to take a term called potential. It's going to be the difference in the strain energy and the external work. All right. Now, ideally, this should be equal to zero if those two are equal. Right. So for virtual work, you just put that lowercase delta on it to be formal. Delta potential is delta strain energy minus delta work, or we could factor that piece out. And for equilibrium, these two are supposed to be equal. So we're going to say that this delta pi should be equal to zero if we have an exact solution. So if we think about it maybe for something like a point load, we'd say delta of U minus force times displacement. Force times that virtual displacement right there, that'll pass through to that. And what we get left with is force is derivative of U with displacement, which is our other Castigliano theorem. We talked about too. We said we could do d energy, d displacement to get force, or we could do energy, d force to get displacement. We see the other one showing up right there. Now, where this is leading up to is our Rayleigh-Ritz method. And this time we're looking for a solution, could be exact or could be an approximate solution to give us a displacement field for beams or torsion or any other kind of members. Usually for beams because they tend to have the most complex shape. So like we did in this virtual work theoretical aspect, we're going to pick a displacement function that meets the boundary conditions. That is, it meets the geometric boundary conditions. So it has to match the displacement and rotation wherever they're constrained. And we just make it a series of terms. So back here in the virtual work formulation, we said if it worked out exactly and we picked an exact answer, this potential should come out to zero. All right. What we're going to try with the approximate methods is to minimize this number. Instead of zero, if we can't quite make it zero with an approximate answer, we'll make it as small as we can. Right. So that's why we went through the trouble of making this little expression up. So for example, maybe let's say we've got a simply supported beam and a bunch of complex loads on it. All right. Some distributed forces and point load and a lot of stuff. So I've got a distributed load across here, and maybe it's a wavy load like that. And if I went the integration approach and tried to do this, I'd get an expression, but it's going to be kind of complex. I'm pretty sure that it's going to sag down, and maybe it'll have some asymmetry to it. But for any kind of loads that are pointing down, whether I've got this and this plus some intermediate forces and who knows what else on there, I could reasonably assume that it's probably, I've got this and maybe I've got an end moment right here and I've got another bigger force right there. If I think in general, it's going to sag down like this. Right? So I could pick a sinusoidal type function, maybe one or more terms. And if I set it to where I get sine of pi at the right end, so some pi over L times a multiplier, then it'll zero out displacement on the right, and then sine of zero is zero, so zeros out displacement on the left. So just one term, half of a sine period, would be a decent approximation for a beam like this. All right, I'm pretty sure it's going to sag down in the middle. I might not get the exact answer, but I'm going to get something in a good ballpark. So however many terms we choose for that is going to have some unknown. The unknown is going to be the magnitude. All right, I'm picking the shape, and what I need to solve for is this magnitude, this constant out in front. If I have 2 terms or 3 terms, I want to do maybe a second or third sine period, that sort of thing. Then I can do that also. But I need to solve for these A's, these constants out in front. So we're going to write out the potential energy, but this time in terms of displacements instead of loads. And then we're going to minimize that energy. So we said before, pi should come out to 0. This potential should come out to 0. But instead, we just need to make it as small as we can. So if we're going to look for where is that potential energy function minimized, right? So I'm going to try and find what value of A gives me the smallest amount of error. That's going to be some kind of local min, right? If I don't pick an exact answer, my potential energy expression versus that constant out in front, it's not going to hit down to zero. It's going to go something like, say, this, right? We're trying to find the value of A that gives me the smallest amount of error here. Usually at some sort of a local saddle point. So I'm looking for when the slope of this function with A is 0. And that's going to be what we need. So let's give this a try. We'll see how it works. We're going to try a couple different methods. We're going to do a polynomial function, which I know I can get the exact answer for. And if it works for that, then we'll try it with a trig series instead. So we've done this one. We beat it to death. We know what the deflection on the end should be already, right? I know that V at L should come out at PL cubed over 3EI, right? It's on the 3.5 slide set. We've integrated up to it, et cetera, et cetera. So PL cubed over 3EI, that's what we expect to get. 1/3 of all those numbers, PL cubed over EI. So let's try out this Rayleigh-Ritz approach, but try it out with our polynomial. So we know we're going to get an exact solution. Then we'll try it with something approximate like the trig series. So let's jump over here and we'll give that a go. All right, so if we're going to set it up as a polynomial, here we've got our cantilever beam. I got P on the end there. And then my V of X function, let's just say we make it some summation of A sub I times X to the I. All right, so that's a good polynomial. So it's going to be like A naught X to the 0, so that'll be the constant. A1 X to the 1 plus A2 X squared plus A3 X cubed plus dot, 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 dot. Now, when I'm picking this function, I've got to satisfy my boundary conditions for geometry. What are the, if I put X here on the left, what's my two geometry boundary conditions here? That is, where do I know the slope and or the displacement? Right, so over here at this end, I know that V at 0 is 0. All right. I also know that from this fixed end that the slope at 0 has to be 0. All right. So let's write out the V prime of X expression. And that one doesn't come down. I got A1, and then I got plus 2 A2 X to the 1 plus 3 A3 X squared plus any other term. Now, for V of 0 to be 0, I definitely can't have this term, right? Everything else in here would 0 out. So these are all good to satisfy this one, right? I can't have that first one, though, so we'll make sure not to use that. For the slope equal to 0, that's these. I can't have this one either. This would 0 out at 0. This would 0 out, so these are okay. So the two of those together, red and blue, which are, oh, purple. So what satisfies both of those are these terms and then any higher order ones. So I can't have a constant in there. I can't have an X to the first because that won't give me what I need for the slope boundary condition. So I need to pick these. And if we look back on the slide deck, we just pointed out PL cubed over 3EI. We kind of already know V at the end, PL cubed over 3EI. I can see it's got a cubic in it. So we probably don't need to go past the third order. So let's try it out with this as our function. All right. So V of X we're going to say some constant a2x squared plus a3x cubed. And that means my v prime of x is going to be 2a2x to the first plus 3a3 squared. So here's what we've got. We're going to try this out for our Ritz approximation for that displacement. Now, before we've been factoring energy as integral m squared over 2ei and then dx, right? And we had an m of x. With the Ritz method, the whole idea is we don't want to have to bother with our free bodies or m of x or anything like that. So what we've just done is we've assumed a deflection shape. We know it's going to go something like that. We can do that with a polynomial, no problem. So v and y are down this way. But remember, ei v double prime is equal to moment. All right, so we can make a substitution in there, and we could also say that we're going to have ei over 2 and then v double prime squared. That also works for us. Looks like we're going to need one more derivative for that. So if I come down there, I'm going to get 2a2 and then plus 6a3 times x. Okay. This is the one, second derivative is what I need to formulate the energy in terms of this function that we've assumed. And it's only got two terms, so it's not terribly bad to work with. So that sets us up there, okay, to get u. Our work term is just going to be right here. I've got v at L. That's how far my load went, and there's my force, all right? So my work term is just going to be the load P applied times V at L. And I've got an expression for V of X. I just plug in L, and it goes here. So I've got this, and then I got this. A little bit messy, but I've got it there. So there's the expression that we had to work with. Our Ritz method says I say pi is U minus W. And then what we're trying to get is d pi d a sub I equal to 0. All right. We're going to have two constants that are in there, so we do need to solve for both of those. So in terms of the way this will look, my d pi partial a sub I equal to 0. Well, I could do the u part first. It's going to be from 0 to L. I've still got the EI out there in front. This is v double prime squared. That's a function of A. So I could take the 2 down, say v double prime to the first, and then partial v double prime partial a sub I. Might make it a little bit shorter expression for us. And then for the minus the work term, partial dA sub I. So it's going to be P here, and then partial of V at L with A sub I. So here's the partial U, partial A sub I, and here's the partial W, partial A sub I. And it doesn't matter what order we go in. We could write out this expression and this expression first, and then take the derivatives, whichever way we want to go. I'm going to skip just a little bit of that stuff and save us the algebra. So d pi dA2, that's the first one. That one equal to 0. And what we're going to get for that one is 2ei 2a2L plus 3a3L squared. And then over here we got minus P L squared. So there's our first expression that we have to work with. It's got A2 and A3 in it. Two equations, one unknown. The other equation that we have is partial pi partial A3 also equal to 0. So we can make that other expression as well, right? In that one, we've got a 6ei out in front. And then we've got A2L squared plus 2A3L cubed. And then from the work term, we're going to get a PL to the third. So I got two equations and then two things that I don't know, A2 and A3. So out of that, if I combine those two, I can solve that A2 is going to come out PL over 2EI, and A3 is going to come out minus P over 6EI.
Professor, you're pulling off the page again.
Thanks. All right, so A2 and A3. Note that A2 lines up with these L to the first, and A3 lines up with L squared. Down here, it lines up with an L squared versus an L cubed. So we're expecting A2 to have an extra length unit, and it does. Same other stuff, so it all combines. Okay, so my expression then for V of X is going to be this stuff, PL over 2EI. There's A2, and that's times X squared, and then it's going to be minus P over 6EI. There's our A3 and X cubed. So minus P over 6EI, and then we have an X cubed. So this goes back to the purple box. There's my expression for V of X. If I plug it in at L, I get a half minus a 6. That's going to be PL cubed over 3EI. So it works out like we thought it would. Now we can see with a polynomial, I've got to deal with another FOIL type setup where I got to take a derivative and multiply them together. And then I got to take two derivatives, one with the first constant, one with the second constant. So once we have more than one term, the utility really starts to go down for us. Right? Ideally, we'd like some kind of a single term, like a sinusoidal type shape, where we don't have to deal with a lot of foiling, and we could quickly get to a result. It may not be exact, but it'll be pretty good. So let's try this once more, but with a trig type approximation. So we came up with a pretty nice number for that one. Now our trig approach, jump back on here. A sinusoidal type curve will get us zero displacement, right? But it won't get us zero slope, right? So if we're thinking about some basic shapes, and remember we've got V going down, right? But I'm going to, just for the sake of looking at a sine curve, all right? A sinusoidal curve, I could go something like this. That has zero displacement, but it doesn't have zero slope, right? I could do a cosine type curve. That has zero slope, but it doesn't have zero displacement, all right? But if, say, we did 1 minus cosine, and I got it to go up this way, if I mirrored it like that, now I've got zero slope and zero displacement, and I do it over a quarter type periods from 0 to pi over 2. That's going to give me my maximum displacement and slope for V going this way. So if I were to plot that right here, it would look just like this, right? With a zero slope, zero displacement, and I'm just going to start down now. Zero slope, zero displacement to start, and then continually curving more slope and displacement. So 1 minus cosine is a nice setup, and we just probably do one of those, all right? And we'll see how good can we make that one. So my V of X this time, 1 minus cosine, and we're going to do pi over 2L and then times X, right? And since we got a constant in there, that'll fall off for the derivative. So we won't see that too much. It won't really cause us any foiling problems. So here's my V of X. Gives me the approximate shape that I want. It's going to go like this for a V pointed down. And X over this way. So V prime, the 1's going to fall away. All right, so I got minus cosine. That goes flips the sign. So I got sine of pi over 2L times x, and then I need the derivative of what's inside. So that's going to be a pi over 2L out here. Right? And then I go down one more time. Derivative of sine takes us to positive cosine. So I get cosine pi over 2L x. And another one of these comes out. So I got pi over 2L squared. All right. Everybody buy that okay? Or agrees with my trig derivative? I'm doing that one on the fly. All right. So of importance, my v double prime is now a single term. That's going to make it pretty easy to plug back in when we go to our expression. Right? So u we had as integral ei over 2 and then v double prime squared dx from 0 to L. Right? So if we bring the stuff out, we got ei over 2 out front. This stuff can come out. It's actually going to be fourth order now because I got v double prime squared. So I got pi over 2L to the fourth out there. And then on the inside, I got cosine squared from 0 to L, pi over 2L times x dx. All right. Looks a little bit imposing, but if we just go to the back of the calculus book, this one will spit out at L over 2. Okay, not bad at all. So I could throw that one in there. And then my total expression then for u is going to come, and don't forget we need an a in front of there. All right. So let me throw that in front, make sure we didn't forget it. We do need some constant for the magnitude. So that means we're going to be left with a squared out here. So that's going to leave us with a squared. We're going to have pi to the fourth, 2 to the fifth. So what does that give us? 32 down here. L down there. And then I have another L over 2 out here. Right. So I've got a squared. I got pi to the fourth. L to the, sorry, that was L to the fourth down here. And then I've got over 64 and L cubed. So there's my expression. It's only got the one A in there. And then my work. Work is going to be real simple. It's just going to be this expression at L. Well, if I plug in there, pi over 2 of cosine goes away. So I just get it's equal to A. All right. So it's going to be the load P and then V at L. V at L, if I evaluate this, this one goes away at L, and I just get times A. So it's going to be P times A, and there's my work. All right. So I got pi U minus W, and then I just need to do a d pi dA equal to 0. We only have one variable, so we just have to do this once. All right. So here's right here. I'll get pi to the fourth over 32L cubed. And then I've got a to the first power out there. And then I got minus P right here. So here's my expression that I have to work with. And I could see that A is just going to equal 32PL cubed over pi to the fourth EI. All right. Remember, before we had PL cubed over 3EI was our exact solution. All right. If I take a look at this 32 over pi to the fourth, that comes out at 0.329. My last sheet there, so I'm going to go off the page. 32 over pi to the fourth, if we crunch through those numbers, we get 329 versus 333. That's really, really close. And this was certainly a much faster setup for you. V double prime had just one term. The derivative went really fast. No foiling. And we only had to take one derivative instead of two, and then two equation, two unknown for polynomial. So I can see I'm not going to be perfect, but I'm going to get really, really close with one of these Ritz approximations to what we're expecting. And best of all, I didn't have to do any free body diagram, right? No working to get M of X and foiling out M of X and all that stuff. All right, so there's our solution, and we see it works out pretty well. Did anybody have any questions about that one? All right, let's jump on back here. So there's our Rayleigh-Ritz method. We've got a summary slide at the end of those energy ones. It's going to be a 7.4. So we can kind of summarize out what we've looked at so far. All right. Specific to what we just went over, there's our potential energy formulation. Okay. It's going to be the internal energy minus the external work. Primarily for beams is what we're going to use this for, because in the other ones, U works out without an integral most of the time. For torsion or axial, we don't need to shortcut much. We're going to save that big M squared by putting in this V double prime, which if we pick a trig term is probably just going to be a single value, right? So EI over 2 and curvature squared. And then our external work, if we have a concentrated force, we plug it in using the same V of X, but just at that location, so at a specific spot. So this will come out as a constant, not a variable. And then I've got any moments times V prime at those same spots. And then if we have a distributed load, like a lowercase p of X, we multiply it by the original chosen displacement function and integrate that. The only time we'd have to do an integration of any difficulty maybe if we had a distributed load. And here's all of our definitions there. So in our Ritz method, once we formulate that, we can take our d pi dA, set it to 0, and solve for what we need. Right. We just saw that this cosine squared for a quarter period works out to L over 2. That's also true if we're using a simply supported beam and we're going 0 to L as 0 to pi. Sine squared from 0 to pi is going to work out at L over 2 also. So our simplest assumptions then for a cantilever beam, we got 1 minus cosine. For a simply supported beam, we could do a single half sine period, and here's the derivative. So for homeworks and for exam, we don't need to waste a bunch of time re-deriving these derivatives. I checked them, I double checked them, so you can jump to those. And then here's the boundary conditions that we're trying to satisfy, and they both work with those setups. All right, rest of the stuff in here, we've got some thermal expansion stuff. That's what we're going to get to at the end of the course. Also in here, we got our dummy load method formalized. We've got all the Castigliano stuff, strain energy for specific cases. And then our full-on formulas. Remember, our special cases, everything with the moment can usually be used with one of these constant load setups. This is the only one. Be careful. Usually have to integrate M squared dx. And then if we have any multi-component structures, we could just add those up. Let's go ahead and take a look at the homework 5 problems that we can do. And then at this point, we'll be all finished up for today. We'll probably finish up pretty early today. We'll save that thermal expansion stuff for next Monday. All right, and that'll be our last new set of material. So let's take a look at our homework set. Last one. We're launching a UUV out of the mission bay on the LCS, and we're using this crane rail at the back. All right. We've got some hydrostatic drag. So our load tension on the line is going to be at this 3, 4, 5 triangle. So back this way, whatever it is, 36.9 degrees, but easy sines and cosines. All right. And here's our section right there. I went ahead and did A and I and all those things for you right there. And we've got our correction factor for including shear as well. So here's all of our stuff to plug in once we have the formula. We want to find the horizontal and the vertical deflections of the end of the beam, right? Using our Castigliano, right? So we want to know those component displacements. We've got a load that's on an angle. So all we really need to do is break this into two pieces. And we can treat them as individual loads, all right? I can have a piece of Y here. That's going to be my 800 pounds. And then I've got a piece of X. So I could, if I break that into two pieces, which is fine because I do have those two components, my d energy dpx is going to give me my axial displacement, and my d energy dpy is going to give me my transverse or vertical deflection. So on here, we got some axial stretch, we'll have some bending energy, and then we'll have some shear energy. Try it with the shear energy and then drop that term off and see how much of a difference it makes. Right. Remember, you've got to leave these variables alone until you get the energy formulated, and then at the end we can plug in. So that's going to let us try our Castigliano method. We'll get to exercise axial, bending, and transverse shear. Next one, we're going to go back to that exhaust duct that had the problems in the torsion homework. This time we're going to figure out that there's a lateral misalignment. In addition to that angular one that we've dealt with before, now we are off by 1/4 inch. The cutout between this deck and this deck is 1/4 inch off. So in this case, I'm rigidly connected at the O3 level. I got a whole perimeter of bolts. I got a whole perimeter of bolts at the O5 level. So with that much coverage, I don't think I'm going to be able to rotate either end of this. So we could treat it as a beam with two fixed end supports. Right. Now that means it's indeterminate twice. I'll need to find out what the reactions are at this end before I could solve everything, because I've got two reactions here, two reactions there, and I've only got two equations to work with in statics, some forces transverse and some moments. But if I use my energy method, my Castigliano, I can say, all right, well, I'll put two of these loads on and treat them like forces. So I'll put a reaction up here. I'm almost sure it's pushing that way. And because I'm frowny faced right here, smiley over here, or whichever way you're looking at from, I'm pretty sure my moment is going to have to go like this. All right. Because I can see the curvature going that way. So I put two loads on here, or I can put them down here, whichever way I want to do it. But let's say up there. So if I go through, get the energy in terms of these two, I can call this reaction force, reaction moment. And then I take the energy, the reaction force, that's equal to delta. But this time I know my delta. It's 1/4 inch. Right. So du, d force is going to give me 1/4 inch. This time I need to solve for the load instead. And my du, d moment is going to give me my rotation. What's my rotation up there? If it's a fixed end. 0, right. So the bolts have got it held. It can't rotate. So I can take du dm equals 0, du df equals 1/4, and then solve for these two reactions, what we don't know. Right. So this gives us a chance to try statically indeterminate with our Castigliano. It can go a little bit quicker, certainly, than the integration of the beam method. And maybe same, maybe a little bit slower than the superposition, but we have it for two variables this time. So you get a statically determinate Castigliano on the first, and then a statically indeterminate there. Third one here, we're going to try statically determinate, but a multi-part structure. Right? So we've got the Tilly crane out on the LHD deck, and we're moving a cargo pallet around. All right. That's going to consist of what we'll call a beam on this diagonal, also in a 3, 4, 5 triangle, and then an axial bar right here with everything pinned together. So in order to solve this one, We'll just need to get the reactions down here at the base of the card and then treat each of these three members as separate. All right. So a little preview. We can go 2P up this way and P down here. Right. Some moments in any of those will get you those reactions. By some moments about the middle, I can see they both got to be P down equal an opposite moment. Or if I look at moments about this right-hand side, I got to have twice as much here because it's closer. And then from that spot, I'm going to make a couple of cuts. I'm going to keep this one and treat this as a beam from 0 to L. I can make a cut down here and keep this piece. And then the axial bar. Take a cut, keep that right there. All right. So axial bar will be constant with 2P going compressive. This one is going to have, just like problem number 1, 80% of P going transverse and 60% going axial, compressing this one and stretching this one, right? We just leave it all as a function of P. For this one, though, get your energies in those. So get an axial and a bending energy for this piece and this piece. Even though this one's compressing and this one's stretching, they'll still come out the same energy. So we'll get double of that. And then we'll get the energy in the axial bar, and we take the energy dP, we'll get the deflection. Then for number 4, we've got a cargo pallet here. It's resting on a couple of rollers. We put it off the crane, and we've got a load that's evenly distributed on the right-hand side of the pallet. All right. We'll do a one-term Ritz approximation. And we want to figure out what is the deflection right here at the center, right? That's going to be just equal to A1 because for a single term, the max deflection goes right through the center. Looks something like this. With the Ritz method. My actual deflection might be just slightly skewed of that. Maybe it's going to look something like this because the load is over there. But we're going to get a pretty good number problem. So try out the one-term Ritz with your distributed load right here. That's a pretty, it's going to be a distributed load, but you're just integrating sine up to cosine, or you can have a calculator do it for you, but it's a simple expression for that. And then figure out what delta at the center is. It should be equal to whatever you found for A1. Then go back and try it with a dummy load, which is going to be, we'll put a dummy force right there and solve it with the M squared approach. All right. That one will take us a little bit longer, but we'll see that these two methods will come out really, really close for that deflection. And then our last one from what we've already covered, number 5 here. We're at this access hatch, trying to get it open with a lug wrench, right? We want to figure out, when we're pulling down with a certain amount of force over here, we want to calculate what's the deflection over there, as well as the rotation as we're pulling down. All right. We're going to watch bending and torsion effects. We don't need to include the shear energy. But that means for this beam right here, I'm going to have a force and a moment on it. So I'll have bending all along this one. All right. When I get over here, my bending moment at the end, which is going to be M naught plus P times L, over here, that's going to act as a torsion on this member. Right. So we're going to have just M of X bending along here. And remember, there'll still be a P force over here. And then when we hand it off to this beam on the backside, that's still going to have the end force doing a cantilever deflection, but it's also going to have the bending moment from this one on the end causing a torsion up here. So this one will have torsion plus bending. This one will have just bending. This is going to be a good one for us to practice a little bit of 3D handoffs. It's about as complex as we do in this class. Okay. Bonus points if you realize we're never going to get that open direction tight. Haven't got a chance to flip for that diagram, but Anyway, this will give us a good chance to try a little bit of 3D handoff between the loads, or you can solve the reactions and do that. But here we can see it's all going to be bending about this transverse axis, the M naught that we put on there plus the P. When we get over here, I got a big bending moment on the end there, and I've also got my reaction, right, that opposes this stuff out here. When I hand that off to this beam, I'm going to have the vertical load still pulling down on it, but now that what was a bending moment will be a torsion over here. So I get a chance to try that handoff. The torsion will be a constant as we go down there, so it's still just T squared L over 2GJ. All right, so get going on those, give them a try. The last of the material for problems 6, 7, and 8, we're going to cover on Monday. That'll be the end of our new material. We'll do some application to fleet issues on Wednesday, and then Monday the 8th, we'll come in and review this last one. All right. So we'll see you guys on Monday. We'll do the last few slide sets. Take a look at these energy problems between now and then and see if you can get started on.